Hi, I'm Toru Tanzawa. Thanks for coming. I'm going to have a series tutorial presentation on charge pump circuits. Please send me email to this address if you have any question. If you have any more interest on this topic, please visit this website. You may find another interesting things. In the previous presentation, I talked about the steady-state circuit equation in low-frequency operation. However, if you extend the operation frequency, the performance may not improve as the frequency increases. So in this presentation, I focus on the frequency response on the charge pump performance. In a low frequency operation model, which is called as the slow switching limit. In that model, the output current increases as the clock frequency. However, it is expected that real behavior should be different from the first approximation. For example, starting at 5 megahertz, this is a current profile during a half clock period. The output current spikes at the beginning of the clock edge, then the charge transferred, then the voltage difference between the two nodes reduces, resulting in the sudden reduction in output current like this. So in this example, the half clock cycle is 100 nanosecond, and the output current sufficient to be reduced down to about 0 during this time period. If you increase the clock frequency, then this current profile could have this kind of behavior, meaning that the half clock period cycle, still you have finite output current component like this. And furthermore, if you extend the clock frequency, then probably the output current is limited by the clock half cycle. So at this point, the amount of a charge couldn't be sufficient to get the sufficient output current. So you would expect that behavior is like this. So let's assume that when you reduce the clock cycle by half, then if you reduce the capacitor size by half, then should we have the output current remain the same? So let's think about plastic capacitance component CS at this node. Then parameter beta is introduced like this. When the clock amplitude is 3 volt, then your capacitor size is 1 picofarad, and the plastic element is 1.1 picofarad. Then this capacitor dividers reduce the actual amplitude at this node by 10%. And therefore, in this example, the effective clock amplitude would be 2.7 volt. And if you reduce the clock cycle time by half, then you may think that the capacitor size reduction by half could remain the same output current with the significantly reduced circuit area. However, this 0.1 picofarad, the plastic element still there, and the capacitor ratios increases to 20%. Therefore, 3 volt amplitude is reduced to 2.4 volt. And at this point, the output current would rather decrease than remain the same. So this is not the true fact. Before moving forward, I'm showing that there is a method to effectively remove the threshold voltage of the transistor out of the charge pump performance. This is called the 4-phase clock charge pump configuration. You have phi 1, phi 2, phi 3, phi 4 like this. And so these two stages are connected in series. And those 4 phases like this. And so starting at this point here, each clock has these state. Then after that, at this point, the clock phi 4 increases high, go high. Then this gate is boosted up so that the transistor operate in triode motion, triode region. Therefore, this transistor can transfer Fourier, and so no VT loss between the two nodes. Of course, in this case, in comparison with the 2-phase clock case, there is there's margins between the two adjacent clock, and so the operational frequency could limit it, and also you have the off time in one clock period. Because we want to have the I out P out equation, which depends on the clock frequency, and therefore you should have the differential equations during clock half cycle. This is the portion at the first stage with input VDD, and this is equation number 1, shows the differential equation for this capacitor node V1. V1 has the waveform like this. At this clock edge, this node goes down, then charged up through transistor's resistance R. And here I marked the V1I, V1T V1F, which show respectively initial and final voltage at V1. And therefore, for those, the steady state condition should be expressed by this, where small q indicate charge that during the transferred from the input VDD to the first capacitor during a half clock cycle. And similarly, you would have intermediate adjacent two stages, and the charge transfer from, and in this example, 2K node to 2K plus 1 node like this, and therefore at this point the clock edge increases this node voltage, then transfer to the next stage. At the same time, this node goes down with the clock edge, then the charge up to this final voltage condition. So that situation is described by this differential equation. And also you have the steady state conditions for those two capacitors like this. And they also in this portions, this is a second half cycle period. Then this tilde indicate this voltage is during the second half cycle. The equation itself exactly same as the previous one. And finally, the last, the switching transistor between the last stage and output voltage terminal have this kind of differential equation. And similarly, this is the steady state condition at the last stage node voltage Vn. And to solve those differential equations, simultaneously differential equations, we should have the additional equations to connect the final state to the initial state. The blue and red dots indicate the final and initial points. And these points are related with this equation. The clock amplitude, when the clock amplitude BDD, and the beta indicates top rate parasitic capacitance divided by the charge bond capacity C. Then the effective voltage amplitude is expressed by this term. And similarly, you can write down those other those. And those three kinds of equation sets sufficient to solve those equations to get the voltage output and current equation. So let's start with the first stage equation here. And if you introduce Xi like this, then you can write V1 final like this. And addition to that, you already have this kind of equation, and from these you get the intermediate the equations like these. And this is equations for the final stage, and you also have this equation. And lastly, these equation number 3 sets plus the previous the intermediate equations get this another form. And finally, you get the final voltage at the even number and odd number relationship, and with the parameter A, which is given by these terms. In addition, you also have the odd and even number nodal voltage relationship like this. The B is expressed by this. Then you just write down for the older terms from k equal 1 through n. Then the old terms have like these kinds of form. Then you just simply add older equations to cancel out intermediate node voltage like this. Then finally, you get the relationship between the last stage and the initial stage and nodal voltage like this. And you can input the final voltage of V1 to here. Then you get this equation for V and F. And lastly, available equation and the previously available equation combined into this equation, which result in this form. So this is the exactly same equations as the equations for under the slow or switching limit or a very low frequency operation. The difference is output equivalent output resistance, which now has a frequency time like this. Vmax is the same as before. So let's look at the output resistance as a function of F. Note that this first time is based on the intermediate stages, and the second term is based on the initial and last stages. So to validate that equation, we learn the spice simulation and measurement based on these parameters. Here's the clock frequency versus output current, and the power conversion efficiency. The SSL and the FSL indicate that the slow switching limit and the fast switching limit. The slow switching limit has output current proportional to clock frequency like this, and FSL indicates when you increase the frequency f to infinity, you get the constant number like this. This bold curve shows a module equation, and this the rectangle marks the measured points. Measured points are limited in terms of clock frequency, and however, in this region, the model has a good agreement with the measured result. And this model suggests that there is optimum clock frequency to maximize output current. So beyond that, not only you lose the output current, but also lose the power efficiency. Let's look at the output impedance in more detail. As you see, if you decrease f to 0, then this term becomes n, and therefore R out is in proportion to f at the slow switching limit, which is expressed by this line. And if you increase f to infinity, then this f term all gone, and the remaining term is expressed by this. This is very intuitive, and because we have R for each resistance, each stage resistance, and we have n+1 diodes or switches, and the factor of 2 is from the charge transfer at every diode is occurring in a half cycle time. So if you average 1 cycle time, then equivalent resistance should be doubled. So this is the fast slow switching limit output impedance, and this line shows this. And very interestingly, I varied the T off time from 10 nanosecond, 1 nanosecond, and 0 nanosecond for this equation. Then with the 0 T off, then as you see, the clock frequency versus output impedance behaves like this. And at the slow switching limit, the R out approaches slow switching limit. And at the very high frequency, the R out approaches and fast to slow switching R out. However, if you consider finite off time, then the actual behavior like this. So at the slow switching limit, all the curves converges to this value. However, at the high frequency, there is another behavior to show the optimum, the minimum, the output resistance point, depending on the T-off. So because of this behavior, the output current in ether behaves like this. As the T of time increases, then the highest I out reduced very significantly. And so this suggests that you should minimize off time to get the maximum output current with the given circuit area. The ether is looks very similar. T off provide the highest clock frequency. Beyond that, the ether suddenly degrades like this. So again, the minimizing the T off should be the design priority. That's it for this presentation. Thank you.